numbers with a particular order or pattern? Each number is called a term. Okay, each number is called a term. We can have two different types of sequences. We can have what we call a finite sequence, and that is a sequence with a limited number of terms. So, for example, our sequence could look like this: 1, 2, 3, 4, 5, and that's it. That's all the sequence consists of. An infinite sequence has unlimited terms, or it doesn't end. So, for example, 0, 1, 2, 3, 4, 5, dot, dot, dot. When you see those dots, that means that it continues on forever. You keep following that pattern. So in this case, you're just counting by ones. That sequence does not end. The first term in a sequence is denoted A sub 1. Sometimes they will use A sub 0, but most of the time they use A sub 1 for the first term. And that's what we're going to use, but don't be thrown off if you see on the final exam they use an A sub 0 instead. Okay, so that little number is a subscript, and that means A represents term, and the 1 represents which term it is. So each subsequent term is denoted A sub n. That n changes, where n is the term number in the sequence. So if I say A sub 5, I'm talking about the 5th term in that sequence. So if we have this pattern 1, 5, 9, 13, 17, let's determine the following term values. So A sub 1, the first term is 1. The 4th term would be 13. Is that a 9? Yeah, the 9th term. So what are we counting by? What's our pattern here? We're counting by 4s. So if we kept going, our 9th term would end up giving us 33, and the 12th term would give us 45. Okay, so we're counting by 4, so 21, 25, 29, okay, so forth and so on. Keeps going. All right. So let's keep looking. Let's look at sequences as functions. Since each term value is paired with exactly one term number, a sequence is a function with the following properties. The domain is the set of the term numbers. Okay, the domain, the x values, so to speak, is what term you're talking about, the first term, the second term, the third term, etc. Your range is the set of the term values. So what is the first term? The first term is 1. What is the second term? The second term is 5. Okay, so think of them kind of like your x's and your y's. In an infinite set, the domain is the set of natural numbers. Natural numbers are just your counting numbers. Okay, that's another way of saying your counting numbers. 1, 2, 3, 4, etc. So it's not all real numbers. We're used to a domain being all real numbers. It's not all real numbers, because all real numbers includes negative values, 0, decimals, fractions, and everything. So we're just talking about our counting numbers or our natural numbers. Okay, now here's some more terminology that we need to make sure we've got. Recursive formula. The recursive formula is a rule in which one or more previous terms are used to generate the next term. Okay, a rule in which one or more previous terms are used to generate the next term. So a very classic example of that is something that we call the Fibonacci sequence. Okay, the Fibonacci sequence, it starts with 0, and then the next number is 1, the next number is 1, then it's 2, then it's 3, then it's 5, then it's 8, then it's 13, 21, 34. Does anybody see the pattern? Okay, you're adding the previous two terms. Okay, you are adding the previous two terms in the Fibonacci sequence. So the recursive formula for this would be a sub n, whichever term I'm talking about, is equal to a sub n minus 1. So n minus 1 would be the one before the one I'm talking about, plus a sub n minus 2, the one before that. Okay, so if I'm talking about the fifth term, I find the a sub 5 by taking a sub 4 plus a sub 3. Okay, so the third and fourth terms give me the fifth term. Okay, does the notation make sense? Because that tends to be what people struggle with the most, is the notation. Is it kind of new? Any questions about it so far? Okay, so let's look at some examples. Oh, by the way, the Fibonacci sequence shows up a lot in nature. Pine cones, pineapples, there's something else. There are a bunch of different examples. They're the little, on the pine cone, what do you call those things? Like the things that stick out. Anyways, whatever, y'all know what I'm talking about, right? They're in a pattern. Okay, they're in a pattern according to the Fibonacci sequence. If you count around, they have a certain number of spirals. You can do it with like the little shapes on the sides of the pineapple. A bunch of different examples in nature where the Fibonacci sequence comes into play. Just one little factor. Okay, let's look at the examples. Find the first 5 terms of each sequence. So they tell us the first term is 14, and we find a sub n by taking a sub n minus 1, the previous term, and adding 9. Okay, in parentheses it says for n is greater than or equal to 2. So that means that's where you start counting. Okay, that's where you start counting. So a sub 2 is equal to a sub 1 plus 9. A sub 1 was 14, so 14 plus 9 is 23. A sub 3, we take the previous term, 23, and we add 9 to it, so that's 32. Okay, so a sub 4, we add 9 again, so that's 41. And then a sub 5, we add 9 again, so we get 50. Okay. Now, the next one's a little bit more, yes, sir? The domain? Well, it does start with 1. It does start with 1, but the parentheses are just, yeah, it starts because a sub 1, they give us a sub 1. We just start figuring it out with number 2 because they gave us number 1. Okay, the second example, the equation there, the recursive formula is a little bit more complicated. It's not just the previous term plus or minus a number. It's 2 times the previous number minus 5. So let's do that. A sub 2 would be 2 times a sub 1, which they told us was 6, minus 5. So it's 12 minus 5, so that is 7. A sub 3, 2 times the previous term, so 7, minus 5. So 2 times 7 is 14. 14 minus 5 is 9. Y'all let me know if I do something wrong. A sub 4 is equal to 2 times the previous minus 5. So 2 times 9 minus 5. 18 minus 5 is 13. And a sub 5 is 2 times 13 minus 5. So 26 minus 5, 21. So what's the pattern there? Okay, it goes up by 1, then it goes up by 2, then by 4, then by 8. So that's kind of interesting that formula will produce that pattern. I find the formulas interesting. Because it's 2 times a sub n minus 1. So if I'm finding a sub 2, 2 minus 1 is a sub 1. So a sub 1 was 6. 2 times the previous term minus 5. So if I'm talking about the second term, the previous term was the first term, they gave me the first term. 6. Yes, sir. Yeah, that means I start with 2. Yes, and I go up from there. Okay? Any other questions? Good questions. Okay, let's do a couple more. All right, number 3. Our first term is 354. Our first term is 354. Our recursive formula is a sub n is equal to a sub n minus 1 plus 6 divided by 3. So we take the previous term, so we start with 2. Okay, the previous term would be the first term, that was 354. So 354 plus 6 divided by 3. So that's what, 360 divided by 3, so 120. Okay, so the third term, we take the previous term, 120, add 6, divide by 3, we get 42. And I'm running out of space, so I'm just going to start writing the terms. A sub 4 is 42 plus 6 divided by 3, so 48 divided by 3 is 16. And if we add 16 plus 6, that's 22. 22 is not evenly divisible by 3, so we'll just leave it as 22 over 3. Okay, now the next one, they give us a sub 1 and a sub 2 because look at the recursive formula. A sub n is equal to a sub n minus 1 times a sub n minus 2. So we're multiplying the previous 2 terms. So this time we're going to start with 3 because they gave us the first 2. We're going to start with number 3. So we multiply the 2 previous terms. So 3 times 4 is 12. A sub 4, we're going to multiply the 2 previous terms. 12 times 4. So that's 48. A sub 5, we're going to multiply the previous 2. 48 times 12. So that is 576. That got real big, real fast. So they gave us the first 2, 3, 4. We figured out 12, 48, and 576. Okay. Pretty simple, right? Just looks a lot different. That's what intimidates people. Okay, let's look at 5 and 6. It says write a rule for each sequence and then give the next 3 terms. So let's look at that first one. We've got 4, 11, 32, 95, 284. Okay, so I always start with, am I adding or subtracting something? So let's see what we're adding. We're adding 7. We're adding, what is that, 21. And 63. And a really big number. 284 minus 95. What'd you say, 189? Thank you. Okay. 189. So what's happening here? Okay, we're multiplying what we're adding by 3. 7 times 3 is 21. 21 times 3 is 63. 63 times 3 is 189. Okay, so we already looked at a similar pattern to that, so I'm going to go back to that problem and see what its formula looks like. Okay, this was a similar thing. We added 1, then we added 2, then we added 4, then we added 8. Okay, so similar kind of process going on there. So we multiplied the previous term by a number, and then we subtracted something. So let's see if we can do that here. What number do we multiply 4 by to get something that's close to 11? 3. Okay, so 3 times 4 gives us 12, so we'd have to take away 1. Let's see if that works for the next one. If we multiply 11 by 3 and take away 1, we get 32. When we multiply 32 by 3, we get 96. Take away 1, we get 95. Let's check it one more time just to be sure. If it's true 3 times, it's probably good.
No problem.
You promise it's true, I don't have to check? All right. I should have believed Brandon and his promise. Okay, that is true. So let's write the rule. We've got to give the first term, a sub 1 is 4, and then our rule, a sub n is equal to, we multiplied 3 times the previous term, a sub n minus 1, and we subtracted 1. Then I want us to get the next 3 terms. Yes, I did. Yeah. You do need to tell where to start at. Because if we had started with 2, our sequence would be completely different. Oh, you're talking about the greater than. Yeah, you don't have to worry about that part. It's pretty understood. If you're given the first term, then you start with number 2. Okay. So our next one is 851. And then 2552 and 7,655. Now, it's kind of an interesting way to do it in your calculator. I don't think I've ever shown this to you, but I knew we've never really needed to do a repeated process before. But I had the last term already as an answer. So instead of typing 3 times 284 and subtracting 1, I did 3 times the answer minus 1. And then I can just keep hitting enter, and every time it will plug in that previous answer. So that's a really quick way to produce some of these sequences. Okay. All right, let's look at the last one. We've got 100, 60, 40, 30, 25. So what's happening? We subtracted 40, we subtracted 20, we subtracted 10, we subtracted 5. So since we're subtracting, our numbers are getting smaller, so we probably need a fraction involved. Okay, Taylor says divide by 2, add 10. Is she right? What do we think? She is right. Okay, we divide by 2. 1/2 times 100, or not 100. I need to put a sub n minus 1. My bad. Or you could do that divided by 2, whichever way you want to write it. And then, so that gives us 50, but we got to get to 60, so we add 10. 60 divided by 2 is 30. 30 plus 10 is 40. 40 divided by 2 is 20. 20 plus 30, or excuse me, 20 plus 10 is 30. Okay, that is true. So let's keep going. We're going to get some fractions here. So let's see if we can make the calculator do it. 25. So the answer divided by 2 plus 10, and I want it to be a fraction. So 45 over 2, 85 over 4, and 165 over 8 would be the next 3 terms. Because I like fractions better than decimals. No, as long as they're equivalent numbers, no. They look so weird. Well, because the reason why I favor fractions is because if you're going to turn around and have to do operations with them, whether it be adding or subtracting, multiplying or dividing, personally, I think it's easier to do that with fractions than it is with decimals. So I just tend to always put things in fraction form. Okay, explicit formulas. So recursive formulas, they'll produce a sequence, but they're a little bit of a pain because You have to know the previous term. If I wanted to know the 100th term in one of these sequences, I would have to figure out all 99 before I get to the 100th term. You have to know the previous term to find one. So recursive formulas are kind of limited in their helpfulness, I guess you would say. So in come explicit formulas. The good thing about explicit formulas is they are rules in which the nth term is defined as a function of n. Don't need previous terms. So the explicit formula, if I was trying to find the 100th term, the explicit formula would be in a form so that I can just put 100 into that formula and it will give me the answer. So for example, number 7 here, a sub n is equal to 7 times n minus 3. Notice there's no a sub n minus 1. It's just a function of its position in the sequence. So I don't have to start with finding the first term. It does say find the first 5 terms, so I am going to. But notice they also don't give me the first term. Okay, they don't give me the first term because the formula here will produce the first term. So a sub 1 is equal to 7 times 1 minus 3. So 1 minus 3 is negative 2. So 7 times negative 2, that's going to be negative 14. So my second term, 7 times 2 minus 3. So 2 minus 3 is negative 1, so that's negative 7. My third term, 7 times 3 minus 3, so that's 0. My fourth term, 7 times 4 minus 3, so that's 7. And what do you think my fifth term is going to be? 14. Okay. So it's adding 7. So I can write a recursive formula for this. My recursive formula would be a sub 1 is negative 14. And a sub n is equal to a sub n minus 1 plus 7. Okay? I can write a recursive formula, but this is a whole lot more helpful if I want to find higher terms in the sequence. If I want to know the 100th term, just plug in 100. 7 times 97, whatever that is, that's the 100th term. Okay? Number 8. This one looks a little bit different. It's 1/3 to the n plus 1 power. So a sub 1 is equal to 1/3 to the 1 plus 1, so that's 1/3 squared, which would be 1 squared is 1, 3 squared is 9. So a sub 2 is 1/3 to the 2 plus 1, so 1/3 cubed is 1 over 27. A 3 is 1/3 to the 4th, so 1 over 81. Nope, not 81. Yes, 81. A sub 4 is 1/3 to the 5th, so 1 over 243. And a sub 5 is 1/3 to the 6th. 729, thank you. That's 1 over 729. So what's happening on this one every time? Multiplying the denominator by 3, so we're multiplying by 1/3 every time. So this one we were adding 7 every time, this one we were multiplying 1/3 every time. We're going to look at, those are some special cases that we're going to focus on here in a minute, but let's look at a couple more just general equations. Okay, if it's negative 4n squared, okay, negative 4n squared, first 5 terms, so a sub 1. I'm sorry, did you have a question?
So the explicit formula is just a regular equation.
Yeah. Yeah. So negative 4 times 1 squared, so that's negative 4. A sub 2 is negative 4 times 2 squared, so that's negative 16. A cubed is A sub 3 is negative 4 times 3 squared, so negative 4 times 9, negative 36. A sub 4 is negative 4 times 4 squared, negative 4 is negative 64, right? 4 cubed. And the fifth term, negative 4 times 5 squared, negative 100. Yes, sir. Yes, we always start with 1. Yes, only apply the counting numbers.
So if we go like one of the things, well, essentially we're gonna have to use the negative.
Nope. Sequences in series, always positive, always the counting numbers. Won't have to plug in fractions, won't have to plug in decimals, won't have to plug in negatives. Now, there may be those things involved in the equation, but you're not going to have to plug them in. Okay? Here's another one. 2n times n minus 5. So we've got 2 times 1 plus 5. So 2 times 6 is 12. A sub 2, 2 times 2 times 2 plus 5. So 4 times 7, 28. You are more than welcome to use your calculator. I'm just practicing my mental math. 2 times 3 is 6. 6 times 8, 48. So 8 times 9, 72. 2 times 5 plus 5. So that's 10 times 10, 100. Okay. Any more questions so far? Doing good? Okay, almost done. Number 11. A sub 1 is equal to negative 2 to the 1 minus 1. What is anything raised to the 0 power? 1. Anything to the 0 is 1. Doesn't matter what it is. If it's raised to the 0 power, it's equal to 1. So that's negative 2 first, which is negative 2. Negative 2 squared would be positive 4. Negative 2 cubed would be negative 8. And negative 2 to the 4th would be positive 16. Excuse me. So that's interesting. That one alternates between positive and negative numbers because the base is negative. Negative numbers to odd powers give negatives. Negative numbers to even powers give positive numbers. Number 12, we've got 1 minus 4 squared. So that's negative 3 squared, positive 9. 2 minus 4 squared, that's negative 2 squared, which is 4. 3 minus 4 squared is 1. Negative 1. Negative 1 squared is 1. 4 minus 4 squared is 0. Squared is 0. 5 minus 4 squared is 1. 1 squared is 1. That one's kind of interesting. What would the next term be? 4. So it's like we started at 9, we're counting down, and then we start counting up again.
Do they all show like symmetry?
Do what?
Do all of them show symmetry?
No, don't have symmetry. There's some kind of pattern. This one has symmetry because it's a quadratic. Think about n minus 4 squared. Think about that being graphed. It's a parabola, so it has that symmetry. They all have a pattern of some sort, but some of them do end up with some symmetry. Okay, now I'm going to let y'all look at 13 through 16. Think about them for a little bit. See if you can come up with a pattern and write an explicit rule. Okay, write an explicit rule that will give each number, and then we'll talk about them as a group.